What about finding the tangent using exactly 1 point? Well, part of the problem with this is if I'm only using 1 point, in this case, determine the equation of the tangent line to the curve of y is equal to x squared at the point of 3 and 9, I obviously can't just use 1 point to solve it based on what we know mathematically, because if I try and use that formula, my slope is equal to 9 over 3 minus y2 or y1 over x1. Well, if I use the same points, I just get 0 over 0, which doesn't really help me at all, and it just cancels itself out. So, in order to find the equation of the tangent, first we need to find the slope. And to find the slope, we need to know 2 points that exist on the line. In this case, we only know 1, so we must calculate an approximation of m by choosing a second point that is as close as possible to the first point. So we're going to say that if P is our first point of 3 and 9, we're going to pick a second point that we're just going to call Q, which is x and y. The second point is a variable point on the graph. It can be any other x and y that it could possibly exist on this graph. In the second point, we have to choose a point where the x value is not 3 so that the point Q and point P aren't the same. Because remember, we're still solving it based on 2 points. And then we can find the slope of PQ or the secant to the tangent line and find the equation of the tangent line. All right, let's start by graphing our first function, y is equal to x squared. So we're going to start with the points we know. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. Or negative 1 squared is 1, negative 2 squared is 4, negative 3 squared is 9. And then we're just going to follow along the curve, graph it out as best we can. And remember that the point of tangency, that point P that we were given, is right up here. P is at 3 and 9. Then we can choose a second point. Anywhere along the graph is going to be a second point that we call x and y, which means that I could say that I'm going to use this as a point to x and y. I could say that I can use this as a point to x and y. Literally any point along this curve is a point of x and y, where if I picked a point, I connected the lines, I could use that as a secant. We are going to choose the unknown point of x and y, and we're going to use our slope formula to state that if my slope is equal to y2 minus y1 over x2 minus x1, and I'm using the points of P, which is 3 and 9, and Q, which is x and y, then I'm going to state that my slope, which is y over x for Q, and 9 and 3 for P, is my starting point. I also know that this goes through the point on the function y is equal to x squared, which means that I have something that can represent what y is in this case. If y is equal to x squared, then instead of saying y, I'm going to replace that with x squared minus 9 over x minus 3, because remember, the point still has to exist on that quadratic curve. From here, remembering our rational functions, we can factor the numerator. So x squared minus 9 is just going to be x plus 3, x minus 3, over x minus 3. And I can pull out the common factor of x minus 3 from the top and the bottom, which means that my slope can be represented just by, x minus 3, not x plus 3. X minus 3 from the top and bottom. Sorry about that. And I wind up with a slope of x plus 3. Now, if we were to use our rational functions, knowing our non-permissible values, then we would know from here that x can't actually equal 3, but we already stated that up here. If I know my slope is represented by x plus 3, then I'm going to find the slope by starting from the left, so values that are lower than 3, or starting from the right with values that are higher than 3, still using the fact that my slope is just x plus 3. So if I pick a point that is to the left and my slope is x plus 3, then if I pick the point of 2 for x, then my slope is going to be 2 plus 3, or 5. If I say that x is 2.5, my slope is going to be 5.5. If I say it's 2.9, it's 5.9. If I say it's 2.95, it's 5.95. 2.99 is going to become 5.99, and 2.999 is 5.999. And logically, we can see that if we're starting from the left below 3, the closer we get to 3, the closer that the slope approaches 6. What if we start from a point to the right, or with an x value that's greater than 3? So we're going to start with 4. If x is equal to 4, and my slope, obviously, is still x plus 3, then if I start at the point of 4 for x, then my slope is 7. If I say 3.5 for x, my slope is 6.5. At 3.1, it's 6.1. At 3.05, it's 6.05. And then 6.001 and 6.0001. And just like when we approach from the left, as we approach from the right, it's going to get closer and closer to a slope of 6. So, no matter whether we start from the left or start from the right, the closer we get to having Q be the same to P, or the closer it is where x gets to 3, we can say that the slope is getting closer and closer to 6. This suggests that the tangent line is, the slope of the tangent line is 6. Now, we express this in calculus by saying that the slope of the tangent line is the limit of the slopes of the secant lines, and we express it using this format. The limit as Q approaches P, or as point Q gets closer to point P, is going to be the slope of PQ, which we just referred to as the slope. So the slope of PQ as it gets closer and closer to the same point is going to be the actual slope of this tangent line. Using the example that we did previously, we're going to say that the slope is equal to the limit as x gets closer and closer to 3. Now, we solved that the slope was x squared minus 9 over x minus 3. This means that the limit as x approaches 3 is going to be, when I factor that numerator, x minus 3 times x plus 3 over x minus 3. We remove the common factor of x minus 3, and all I'm left with is the limit as x approaches 3 is just that x plus 3. If x is trying to approach the point of 3, then that means that 3 plus 3 is equal to 6, so our slope is equal to 6. Now that we know the slope of the tangent line, we can actually sketch the graph with both that y is equal to x squared, 0, 0, 1, 1, 2, 4, 3, 9, negative 1, 1, negative 2, 4, negative 3, 9. There's a curve. The point of tangency is at 3 and 9. And we're going to use that slope to graph it out. So I have a slope of 6, or 6 over 1. I obviously can't go up 6 and right 1, so I'm going to go down 6, 1, 2, 3, 4, 5, 6, left 1. And there's another point that exists on this tangent line. And 1, 2, 3, 4, 5, 6, and 1. And then ideally, I'm going to use a ruler or a straight edge to extend this off into positive and negative infinity. Now that I know what my line looks like, I can use my slope, I can use my point, and I can use my slope point form to create the equation of the tangent line. I'm going to say that if my point is 3 and 9, and my slope is 6, there's my x, there's my y. My slope point form is y minus y1 is equal to m bracket x minus x1, and I'm just subbing in my values. Y minus 9 is equal to slope of 6 times x minus 3. I expand it out and get rid of the brackets. Y minus 9 is equal to 6x minus 18. And if I want it in slope-intercept form, I'm just going to add 9 to both sides. Y is equal to 6x minus 9. There's my y is equal to mx plus b form. If I want it in general form, then I'm going to move the y over and get 6x minus y minus 9 is equal to 0. And there is my equation for the tangent line. All right, that's it for the first lesson.